Performance of induction motor driven by 3-level neutral clamped inverter using space vector modulation as voltage control technique. Abstract. This paper deals with the performance of induction motor which is driven by a 3-level neutral clamped inverter using space vector modulation technique as voltage control strategy. SVM has increasing applications in power converters and motor control. Compared to other modulation techniques, space vector modulation technique has the advantages like higher modulation index, utilizing DC bus voltage more effectively, generating less THD and thus less harmonics and low ripple content. In this paper, DC voltage is given as input to the 3-level neutral clamped inverter. This inverter has been designed and implemented in MATLAB/SIMULINK software. IGBTs are used as active switches. The triggering pulses to these IGBTs are given by using space vector modulation technique. By selecting proper switching states and by calculating the time period in particular switching state AC voltage with less THD, low dV/dt is obtained as output. AC output of this inverter is given as input to the induction motor. After simulating, the output parameters of induction motor like torque, speed, load current is studied. Keywords: induction motor, IM, neutral clamped inverter, NCI, space vector modulation technique, SVM, total harmonic distortion, THD. Introduction. Multilevel inverters are gaining importance in high power and high voltage applications like manufacturing industry, transportation, renewable energy, and in reactive power compensation due to their superior performance compared to 2-level inverters. If we use 2-level inverters in high voltage and high power applications, the rate of rise of voltage, dV/dt, is significantly high, the switching losses will be more and also there will be constraints of device rating 1. Hence, multilevel inverters are becoming popular which produce high power, high voltages without requiring transformers or higher rating individual devices. Multilevel inverters produce higher level voltages with low dV/dt, low harmonic content and low ripple content 3. The only disadvantage of this technique is that by increasing the levels, the number of switches will increase, and the switching combination will become complex and control will become complicated and expensive 9. Its various applications are in renewable DC source utilization, uninterruptible power supplies, UPS, power transmission through high voltage DC, HVDC, variable frequency drives and electrical vehicle drives 1. The multilevel inverters are classified into 3 types. 1 neutral clamped multilevel inverter. 2 flying capacitors multilevel inverter. 3 cascade H-bridge multilevel inverter. 2 neutral clamped multilevel inverter. Neutral clamped multilevel inverter is also known as diode clamped multilevel inverter. Circuit diagram of a 3-level neutral clamped inverter is shown in the Fig.1. An M-level inverter with one leg consists of M1, DC bus capacitors, M1, M2, clamping diodes and 2, M1, main switching devices. Thus, a 3-level neutral clamped inverter with one leg consists of 2 DC bus capacitors, 2 clamping diodes and 4 main switching devices. Therefore, for a 3-phase, 3-level neutral clamped inverters there are 2 DC bus capacitors, 6 midpoint clamping diodes, 12 main switching devices 1, 4, 5. Table.I shows the switching states of 3-level inverter. Each phase has 3 output states, P, O, and N, corresponding to positive voltage, plus, 0 voltage, 0, and negative voltage. Take phase A as an example. If switch SA1 and SA2 are turned on, then phase A is on P state. If switch SA2 and SA3 are turned on, then phase A is on O state. Similarly, when switch SA3 and SA4 are turned on, then phase A is on N state. Switches S1X and S3X are complementary and switches S2X and S4X are complementary. If one of the complementary switch pairs is turned on, the other of the same pair must be off. 2 switches are always turned on at the same time 3, 4, 5. 3 Space vector pulse width modulation technique. Space vector pulse width modulation technique is a voltage control technique used in inverters which is used to regulate voltage of inverters, cope up with variations of DC input voltage and maintain constant voltage and frequency. Voltage is controlled in each sampling period by space vector transformation concept 1 by I. Properly selecting the switching states for the inverter and 2. Calculation of appropriate time period for each state 4, 7, 8. Since 3 kinds of switching states exist in each phase, 3-level inverter has 33 equals 27 switching states, out of which 3 are null states, and remaining are active states 3, 7. But we consider only 19 states to avoid redundancy and memory wastage in MATLAB 10. From Fig. Point 1. The resultant output load phase voltage of inverter is 4. By substituting the values of VAO, VBO, VCO we can find the voltage vector magnitudes and phase angles of all switching states 1, 10 as shown in Table 2. Table 2. All switching states with their corresponding voltage vectors, magnitude and angle. Switching states. Corresponding voltage vectors. When all these switching states are represented in space by using space vectors, then we get a hexagon with 6 sectors 3, 6, and with 4 subsectors in each sector as shown in Fig. Point 2. A space vector modulation algorithm. Steps to execute SVM logic in MATLAB/SIMULINK are as follow. Step I. Give 3-phase sinusoidal input voltage VA, VB, VC. VA equals VM sin 5. VB equals VM sin, WT 120 6. VC equals VM sin, WT 240 7. Step 2. The coordinate transformation from the ABC axis to the ASS axis. The transformation from the ABC axis to the ASS axis, which is rotating with an angular velocity of, can be obtained by Clerk and Perk transformations as shown below. Here A axis is direct axis, real axis, and SS axis is quadrature axis, imaginary axis. Step 3. Calculate the value of deta, D, and reference voltage, VREF, which is given by. This reference voltage is selected as control instruction, which rotates in the space with an angular frequency. When we consider the reference vector in one of the 6 sectors, 2 active space vectors nearest to VREF is selected along with one of the 3 null vectors by means of their corresponding operating times 7, 8, 10. Step 4. Selection of sector in which VREF is considered. Let n be the sector. As there are 6 sectors, n can be from 1 to 6. N is the function of deta, d, 9. The sector in which the command vector VREF is located, is determined as follow. If d is between 0 degrees and 60 degrees, then VREF is located in sector 1, n equals 1. If d is between 60 degrees and 120 degrees, then VREF is located in sector 2, n equals 2. If d is between 120 degrees and 180 degrees, then VREF is located in sector 3, n equals 3. If d is between 180 degrees and 240 degrees, then VREF is located in sector 4, n equals 4. If d is between 240 degrees and 300 degrees, then VREF is located in sector 5, n equals 5. If d is between 300 degrees and 360 degrees, then VREF is located in sector 6, n equals 6. Step V. Selection of sector angle. Let be the sector angle. Sector angle is the function of deta and n. The value of sector angle is given as follow. If n equals 1 ie, in sector 1, equals d. If n equals 2 ie, in sector 2, equals d 60 0. If n equals 3 ie, in sector 3, equals d 120 0. If n equals 4 ie, in sector 4, equals d plus 180 0. If n equals 5 ie, in sector 5, equals d plus 120 0. If n equals 6 ie, in sector 6, equals d plus 60 0. Step 6. Selection of subsector. Let y be the subsector. Y is the function of VDC, VREF, and sector angle, dot. In each sector there are 4 subsectors, y can be from 1 to 4. Subsector is selected by using modulation index, MI. Modulation index differs from modulation to modulation and from inverter to inverter. For space vector modulation technique, the modulation index is given by m equals 23, 12. From above figure, by using trigonometric ratios we get m1 equals m2v3 sin 3, 13. m2 equals m2v3 sin 14. Y equals 1. M. Y equals 2. M10.5, M20.5 and M1 plus M2, greater than 0.5. Y equals 3. M2 greater than 0.5. Y equals 4. M1 greater than 0.5. For simulation, the MATLAB /SIMULINK diagram of 3-phase, 3-level neutral clamped inverter connected to an induction motor is shown in Fig. Point 6. The input given to the inverter is DC voltage and the output voltage of inverter is given to the 3-phase induction motor. The output voltage of inverter is observed in the scope using voltage measurement blocks. Output parameters of induction motor i.e., torque, speed, and load current are observed in the scope. In MATLAB software, three-phase induction motor is available as asynchronous machine, implements a three-phase asynchronous machine modeled in a selectable DQ reference frame. Stator and rotor windings are connected in Y to an internal neutral point. In SVM block, three-phase sinusoidal voltage is given as input. The output pulses obtained from all sector switching block are compared with the triangular pulses, and the resultant pulses generated by SVM block are given to the IGBTs in the inverter by using Goto and from blocks. These IGBT switches are used to control the output voltage. Parameters: DC input voltage of inverter equals 400 V. Output frequency equals 50 Hz. Induction motor rotor type equals squirrel cage. Number of poles in the induction motor equals 4. Inertia of induction motor equals 0.0131 J, kg.m2. Rated power of induction motor equals 4 kW, 5.4 HP. Rated speed of induction motor equals 1430 rpm. Stator resistance of induction motor equals 1.405. Rotor resistance of induction motor equals 1.395. Stator inductance of induction motor equals 5.839 mH. Rotor inductance of induction motor equals 5.839 mH. Mutual inductance of induction motor equals 0.1722 mH. V. Simulation results. The output voltage of three phases of three-level neutral clamped inverter by using space vector modulation as voltage control strategy is shown in Fig. 7. The FFT, fast Fourier transform, analysis is used to calculate the total harmonic distortion present in the output voltage and output current of inverter. The FFT analysis of output current of three-phase, neutral clamped three-level inverter for space vector modulation is shown in the Fig. 8. The waveforms of electromagnetic torque, T, speed, W, and three-phase current, IOG, of induction motor are shown below in Fig. 9. In MATLAB/SIMULINK, a step input, magnitude of 10 from 0 SEC to 1 SEC and magnitude of 20 after 1 second, is given to the torque terminal of induction motor. Initially the magnitude of torque is 10 Nm and at 1 second the torque magnitude is increased from 10 Nm to 20 Nm as shown in Fig. 9. As a result, the magnitude of speed decreases and current increases at 1 second 10. 6. Conclusion. In this paper, the performance of induction motor which is driven by a three-phase, three-level neutral clamped inverter using space vector modulation technique as voltage control strategy has been studied. A MATLAB/SIMULINK model for implementation of SVM is presented. The step-by-step algorithm of SVM is reported. The speed, torque, and output current of the induction motor, the output voltage of the inverter have been plotted. From the above results we observe that the THD value of output current of three-phase, three-level neutral clamped inverter with space vector pulse width modulation technique is less than 5%, i.e., 2.01%.